Let us discuss the next topic of Module 5, version space. It is a concept learning process accomplished by managing multiple models within a version space. It is a hierarchical representation of knowledge that enables to keep track of all the useful information supplied by a sequence of learning examples without remembering any of the example. The goal is to produce the description that is consistent with all positive example but no negative example in the training set. This is the frame representation of an individual car. We can learn the concept that have to do with the car manufacturers. Here, the fields of the car having origin, manufacturer, color, decade and type. Representation language for car is as shown below. The origin belongs to Japan, USA, Britain, Germany, Italy and so on. Then the manufacturers belongs to Honda, Toyota, Ford, Chrysler, Jaguar, BMW and so on. Color belongs to blue, green, red, white. Decade belongs to 1950, 1980, 1970, 1980, 1990 and 2000. The type belongs to economy, luxury, sports. The concept description as well as training example can be stated in terms of those slots and values. For example, concept Japanese economy car can be represented as origin Japan, manufacturer X1, color X2, decade X3, type is economy. The name X1, X2, X3 are variables. The presence of X2, for example, indicate that the color of a car that is not relevant to whether the car is Japanese economy car. Before proceed to version space algorithm, we should make some observation about representation. Some descriptions are more general than others. For example, description of figure 1 is more general than the description of figure 2. This representation language defines the partial ordering of the description. This is called partial ordering. The entire partial ordering is called the concept space. We can represent the concept space in the another way. So that is at the top of the concept space. This is the partial ordering. The entire partial ordering is called concept space. The top of the concept space is a null description. It consists only the variables that are at the bottom are all possible training instances which contain no variables. Let us look into this slide. Here the entire thing is called concept space. The top of the concept space is null descriptions. It is only described by variables. At the bottom, these are the training set. These are the training examples. Before receive any training example, we know that the target concerns lies somewhere in the concept space. Our target is in the sense version space is located somewhere in the concept space. The current hypothesis can be represented as a subset of concept space is called version space. That means the entire partial ordering is called concept space and the subset of concept space is called version space. The version space is a target collection of description that is consistent with the all training example. The training example can be either positive or negative. The version space simply a set of descriptions. So an initial idea is to keep on explicit list of descriptions. Contains two subsets. One is S specific and G is generic. G contains the most general description consistent with the training example. The version space is a set of all descriptions that lie between some element of G and some element of S in the partial order of the concept space. Each time we receive the positive training example, we want to make S more general. Negative training example received to make the G more specific. If S and G sets converge, our range of hypotheses will narrow to a single concept description. The algorithm for narrowing the version space is called the candidate elimination algorithm. Just look into this slide. Here, the subsets of version space are G and S. G will be more specific once the negative example receives. S will be more generic once the positive examples will receive. This is candidate elimination algorithm. Given a representation language and a set of positive and negative examples expressed in that language, the input will be some positive and negative examples. I will discuss what is positive example and what is negative example. Then compute a concept description that is consistent with all the positive examples and none of the negative examples. First step, initialize G to contain one element, the null description. Initialize S to contain one element, the first positive example. Accept a new training example if it is a positive example. First, remove from G any descriptions that do not cover the example. Then update the set to contain the most specific set of description in the version space that cover the example and current element is of the S set. Then in this positive example, H should be update. H should be update, that should be more generic. That is, generalize the element of S as little as possible so that they cover the new training example. If it is a negative example, first remove from S any description that cover the example. Then update G set to contain most general set of descriptions in the version space that do not cover the example. Then update G. G should be more specific. So this is specialize the element of G as little as possible so that the negative example is no longer covered by any of the elements of G. If S and G are both singleton set, then if they are identical, output their value and hold. If they are both singleton set but they are different, then the training case will be inconsistent. Output this result and hold. Otherwise, go to step 3. So this is all about candidate elimination algorithm. So here we have to remind two things. Is a version space having two subsets G and S. Whenever a positive example comes, then it should be make updation in S itself. Then H should be more generic. Then whenever a negative example met, updation will be taken place in G. By that time, G should be more specific.